Okay, today we're talking about, we're on chapter 13, homeostasis. So we're going to talk about homeostasis, okay? All right, keeping ourselves alive. An individual cannot live unless they can stay warm, find food, and find water. The body maintains an elaborate monitoring system to ensure that the individual is aware of his thirst, their warmth, and their hunger. It is so important to the body that the body maintains several means of monitoring for each system, and this is known as a redundancy. The nervous system coordinates these regulatory systems. The brain closely monitors temperature, water supply, and nutrient supply by using a variety of neural and hormonal mechanisms to keep them within the critical range. If we have excess of any of the three, our bodies have ways of shedding the excess to maintain our level of homeostasis. This is usually done without our knowledge or without even having to think about it. Seeking either shelter, food, or water is to seek a primary need. This type of behavior is known as motivated behavior. The systems used to regulate temperature, body fluids, and metabolism are negative feedback systems. When an individual goes beyond a set point in the level for one of the primary needs, the brain is informed of the negative level, like a warning light on a gas gauge. Because we are constantly burning fuel, utilizing and breathing out liquid, and entering into different environments, the process of maintaining homeostasis is a constant balancing act. I find this really kind of interesting because I see people, even in the dead of winter, who are not wearing coats, they don't have a hat on, they're walking around in shorts. I was at the polling place yesterday. I'm a poll watcher, and an individual came in flip-flops and shorts. Well, it was 40 degrees yesterday, and this guy came in shorts. He had a short sleeve shirt on, he had a pair of shorts on, and he was wearing flip-flops. And I was thinking, everybody else is coming in coats and sweatshirts and hats because it was so cold. But this guy had probably gotten into his car in his heated garage, had driven to the polling place. The only cold weather that he experienced was going from his car into the building, into the polling place, and he probably parked as close to the as close to the building as possible. So he had no idea what the temperature was. He probably spent all of 2 or 3 seconds in that environment, and for that reason, he may keep his house at 75 or 80 degrees. Who knows? It's some people are that way. My daughter's that way. She likes hot weather better than cold weather. She lives here in Iowa, and so she keeps her house pretty warm, and she wears lots of clothes. She's always dressed pretty warm, fairly warmly, especially in the wintertime. Losses that we must have that we cannot get around are known as obligatory losses, and they obviously require constant monitoring of primary need levels. Cooling not only slows the action of molecules, but it slows the chemical reactions in cells as well. Enzyme systems in most mammals and birds are most efficient at normal temperature. Normal temperature for dogs is like 101 degrees. Normal temperature for humans is 98.6 degrees. That's the average. My normal temperature is somewhere between 96 and 97 degrees. Uh, what does that mean? I'm a cold-hearted person. Maybe. No, not really. It just means that my normal temperature is a little bit lower than that. Any higher temperature and protein molecules do not bind properly and thus cannot function as they should. At very high temperatures, the amino acids and the proteins break apart and begin to fuse together at random. The protein in the brain is especially susceptible to high temperatures. Prolonged high fever can cause brain centers that regulate heart rate to die, thus killing the patient. I had a lab officer when I was in the service. He had children who were very sensitive to temperatures. So if they got sick, they had to start feeding them. They didn't have ibuprofen at the time, but they had acetaminophen and aspirin, and so they had to feed them an analgesic to keep their temperature from getting too high, because if it went over 100 degrees, they would go into seizures. They'd start having seizures. So they had to be very, very careful of these children to make sure that they didn't have high temperatures. At very low temperatures, the cellular membranes are disrupted by the formation of ice molecules, and even when thawed, they cannot reform properly. This is one of the reasons why you can't really freeze humans and then thaw them out and they come back to life. It doesn't work that way. Warm-blooded animals generate heat from the inside to keep themselves warm and thus are referred to as endotherms. When we lived up in Montana, we had 2 horses. If we were if it was a really cold night, and it got cold up there a lot, we had temperatures that were below zero on a fairly frequent basis. It got as cold as below 40. We had below 44, minus 44 degrees below zero a couple times. And so, how in the world do you keep your horses from freezing to death? And the answer is you just feed them more food. And the more food that you feed them, of course, they burn that food and it creates heat. And you would see them standing in the corner of. We had a pole barn that faced north. It faced north. So if it was an east wind or a west wind or a north wind, those sides were protected, and they would stand in the corner of the barn, and they would stand together, so they would trade heat back and forth. And of course, they're generating heat the whole time. And you go in there, and it'd be minus 20 degrees, and they'd both be standing in the corner just as warm as toast, and you could see the steam coming off of both the horses. The endotherms generate heat by burning food in the body, a process known as metabolism. Heat inside the body is measured in kilocalories. But the one thing we had to do was make sure that they had a lot of food to eat, or you can't give them too much food, of course. But we had to make sure that they had extra grain. We normally fed them hay and with a little bit of grain. But in the wintertime, the colder it got, the more grain we fed them. 1 kilocalorie is enough heat to raise the temperature of 1 liter of water 1 degree centigrade. An adult can burn as many as 600 kilocalories per hour with strenuous exercise, but only 60 kilocalories when resting. At rest, the brain accounts for 1/3 of the heat generated by the body. As activity increases, the brain continues its level of heat production, but the muscles can increase the heat production tenfold. Humans can create heat by increasing their metabolism, by breaking down brown adipose tissue, by shivering, and increasing blood flow by constricting blood vessels. Brown adipose tissue, which is the stuff on top, actually both of those are pictures of brown adipose tissue, but this is stained differently so it looks brown. Brown adipose tissue is found around vital organs in the thorax, around the cervical and thoracic levels of the spinal cord. Under cold conditions, the sympathetic nervous system stimulates metabolism within brown adipose tissue, producing heat. Humans start shivering at 36.5 degrees centigrade, which is 97.7 degrees Fahrenheit, which starts in the face and spreads downward. So if you've ever been cold, and I'll tell you, it was really cold today. We went to see my grandson's flag football game. He's only 8 years old. But we sat out there, and it was cold, and it was windy. We started shivering, I can tell you. We didn't really dress as warm as we probably should have. And I can assure you that you start shivering from your face and it goes down to the rest of your body. When the human body is hotter than is safe for the individual well-being, brain cells can very quickly be adversely affected if the temperature isn't controlled. The body can cool itself through accelerated respiration, panting, perspiration to cool the skin, dilation of blood vessels to release heat through the skin's surface. And of course, you guys experienced a lot of excessively hot weather where the temperature was well over 110 degrees. On several occasions this summer, I guess not so much up in Saley, but down in Tucson and Phoenix, they had temperatures that were over 110 degrees on several different occasions. And of course, at that point, it's very difficult for you to stay cool. A lot of people just stay inside. They don't go out in the heat, in that kind of heat anyway, because it's dangerous. Actually, you can die in that kind of heat. The human body doesn't seem to have just one thermostat, but three. One of the thermostats is the hypothalamus, and this is the hypothalamus right here. The skin surface, so this is the skin surface, and the body's core, and this is the core right here. Your core is everything but your arms and your legs, and this is your core temperature. And this is one of the reasons why when somebody dies and we're trying to figure out when they died, one of the things we'll do is we will take their core temperature. And the way we do that is with sticking a thermometer into their liver. The liver is right in the center of the body, right in the center of the thorax, and so we can tell how much they have cooled down. As soon as you die, your metabolism stops, and because your metabolism stops, you stop that endothermic reaction. You stop creating heat from within. At that, you know, you start losing heat depending on what the ambient temperature is, depending on what the temperature is outside. And we can tell from taking the ambient temperature, and there's a formula that you have. The temperature you have when they find you, your core temperature, and the ambient temperature, the temperature of the air around you. They can tell how much you have cooled off, and how long you've been dead. As evolutionary biologists point out, humans have the same concentration of salt in their body fluid as the oceans of the world. It is therefore assumed that humans evolved from creatures in the sea who had to maintain a fluid and salt content similar to that of the sea. Thus, humans, as all animals, must not only monitor fluid levels, but salt levels as well. I need to take a drink just a second. Sorry. Osmosis is a special case of diffusion. In this case, a large molecule like starch is dissolved in water. The starch molecule is too large to pass through the pores in the cell membrane, so it cannot diffuse from one side of the membrane to the other. The water molecules can and do pass through the membrane. Hence, the membrane is said to be semi-permeable, since it allows some molecules to pass through, but not others. And this has a lot to do with how medicines work. Medicines tend to be a solute. They tend to be fairly large molecules. And for that reason, sometimes they just will not go through, they will not pass through a membrane like water does. And if they can't get to the place that they're supposed to help. Except for deionized water. And so what do? They attach themselves to a protein that can go through. And then they have to open the pores larger. And that's how they get through. Except for deionized water, other forms of water that we might take into our bodies is in the form of a solution, a mixture of molecules of a solid molecule and water molecules. So solution in this case is referred to as a solvent, and the solid dissolved in it is referred to as a solute. Semipermeable membranes will block the passage of the solute, but allow the water molecules to pass freely from one side to the other. The force or pressure to pull water across a semipermeable membrane is known as osmotic pressure. We refer to the concentration of solute in a solution as the solution's osmolality. Sodium chloride is a solute that the human body must balance in order to maintain a proper fluid balance. The human body must maintain a proper level of sodium chloride in order to function properly. That level of sodium chloride is 0.9%, 9 grams of sodium chloride dissolved in a liter of water. This is referred to as an isotonic solution or as normal saline. Saline means salt water. So if you go into the emergency room and they think that you're dehydrated, one of the things they'll do is they will give you salt water. Oh, there you go. A person who arrives in the emergency room severely dehydrated must be given fluids to replace fluid rapidly. But if they just gave the person water through an IV, it would rapidly adjust the osmolality. Therefore, the medical personnel would administer normal saline to the patient to replace their fluids. In this case, the individual probably has more sodium chloride in their system than they need, and it is said to be hypertonic. Too much water and not enough sodium chloride would be hypotonic. And of course, this changes what your blood cells look like. This is what this is what a normal blood cell looks like. As you can see, it looks a little bit like a donut. So if we put too much salt in the water, this is what happens to that cell. Starts looking like this. If we put too much water in your system, it starts looking like this. If we put way too much water in your system, then your red blood cells will rupture. They will expand to the point they will fill up with water is what they're doing. They're filling up with water and they will rupture. And if that happens, of course, it's really kind of hard to stay alive unless they get to you fairly quickly. And this is what can happen. Some people, when they start a marathon, they think, geez, I hate to stop at those water stops, so I'm going to hyperhydrate. I'm going to drink lots and lots and lots and lots of water. Well, that you can do that, and of course that water will go into your system. A lot of it you will urinate out. But if you're not careful, if you don't monitor it, then one of the things that will happen is this. And that's called hypernatremia. Where you have put too much water in your system, and it kills people. It kills people at marathons. Just about every marathon, you'll have somebody who tries to hyperhydrate, and they'll run for about a mile, and then they'll just drop down dead. And this is the reason why. So this is one of the reasons why you shouldn't drink too much water. Normally, we can't. We just can't do that. Because your stomach will get full and you just don't want to drink anymore. You're hyperhydrated and you just will not. Your body tells you to stop it, stupid. Internal cues that trigger thirst: hypovolemic thirst, thirst caused by low volume of fluid. Baroreceptors in the major blood vessels detect any pressure drop from fluid loss. Usually, it's caused by rapid loss of body fluids, such as hemorrhaging if you're bleeding, diarrhea, or vomiting, and your body will tell you that you need to take in more fluids. Osmotic thirst: high volumes of solute in the extracellular fluid. Osmoreceptors in the brain detect any increased osmolality of extracellular fluid. Hypovolemic thirst: when baroreceptors detect a drop in blood pressure from tension on the artery walls. The information is relayed to the autonomic nervous system. The blood vessels constrict to maintain proper pressure for consciousness. The brain also releases vasopressin, which is it's an antidiuretic hormone from the posterior pituitary gland. Vasopressin acts on the kidneys to reduce flow of water to the bladder, and this is normally what happens if you're in the desert for an extended length of time. When we were when the military was out in the desert, one of the things they did was carry camelbacks. They carried the water on their backs. But another thing they would do, and people will tell you if they've ever been out in the desert for an extended length of time, they didn't have to urinate. One of the reasons they didn't have to urinate was because vasopressin was acting on the kidneys and reducing the flow of water to the bladder. Sometimes when I have been working outside in the heat and I've been sweating a lot, I will drink a lot of fluids, but I won't urinate, and the reason is because of the vasopressin. And I'll go all day long without urinating. As a matter of fact, that's what happened today. I didn't have to urinate for one reason. Oh, I ran today. That's why. Okay. I ran 3 miles this morning. I was sweated pretty good. Hypovolemic thirst in diabetes insipidus. Vasopressin is not produced, and the kidneys will not retain water. The patient is constantly thirsty. They drink a lot of water and they urinate constantly. The urine tends to be almost completely clear because there's nothing in there, and it's not yellow, it's clear. The kidneys also detect low blood volume and release a hormone called renin. Renin triggers a protein called angiotensinogen to form the protein and angiotensin 1, which in turn becomes angiotensin 2. Angiotensin 2 constricts blood vessels. It triggers the release of vasopressin. It triggers the release of aldosterone. It acts on the preoptic area of the brain to elicit the feelings of thirst. This is accomplished in the subfornical organ, one of the circumventricular organs around the open areas or ventricles of the brain where the blood-brain barrier are weak. Osmotic thirst is more common than hypovolemic thirst, as the name suggests. It has to do with an imbalance of sodium chloride in the extracellular fluid due to loss of water. Osmotic thirst is caused from perspiration, from respiration, from urination. Since we are dealing with an increase of sodium chloride in the system, this form of thirst can be triggered by eating salty foods. Research shows that humans have osmoreceptors in various areas in the preoptic area, the anterior hypothalamus, the supraoptic nucleus, the organum vasculosum of the lamina terminalis. These are all in your brain. Sodium chloride balance in the body is very delicate. As we have noted before, hypertonicity or hypotonicity will cause cell destruction. When angiotensin 2 is released in the blood stream, it acts on the adrenal glands to release the mineralocorticoid steroid hormone aldosterone. Aldosterone acts on the kidneys to conserve sodium, which in turn allows the individual to conserve water in the body. The more sodium you have in your body, the more H2O you will also have in your body. And this is one of the reasons why they tell you if you want to lose weight, it's not very good to consume lots of sodium because it will make you retain water. However, humans cannot drink seawater. It is hypertonic and thus adds more salt than water, causing greater thirst. While humans have not evolved to handle hypertonic conditions, creatures that live in the ocean or are able to survive with little water have kidneys that can handle large volumes of sodium chloride. Not only do organisms require water and warmth to survive, but they need food as an energy source. If this were the extent of our needs, humans could eat raw glucose and live very well. However, humans also require nutrients, chemicals that do not provide energy, but are required for the proper functioning of the body. Some of the nutrients that we require are in the form of amino acids. Of the 20 amino acids required by the body, 11 are manufactured internally, so we don't have to worry about those 11. But there are 9 that must be attained through our diet. These 9 are called the 9 essential amino acids. Besides the essential amino acids, our bodies require 15 different vitamins, several minerals, and a few fatty acids from our food. These nutrients are obtained when the body breaks down complex foods into simpler forms through the process of digestion. Most animals, especially humans, will build up stores of nutrients in their body. This is done because our anthropologic ancestors tended to go through cycles of feast and famine, and the individual who could not establish stores of excess nutrients, usually in the form of fat, would not survive to reproduce. All the energy we need to move, think, breathe, and maintain body temperature is derived in the same way. It is released as the chemical bonds of complex molecules are broken from smaller, simpler compounds. To raise body temperature, we release the bond energy as heat. The amount of energy used is expressed in kilocalories. While not all foodstuffs provide energy, that which cannot be used is excreted, especially as solid waste. Available energy is used in one of 3 activities: either processing of newly ingested food, about 33% of energy utilization; basal metabolism, maintaining the body, about 55% of energy utilization; and active behavioral processes, about 12%. Now, if you're trying to lose weight, here's the reality. When you go to bed at night, if you weigh yourself before you go to bed at night, and then weigh yourself when you get up in the morning, you should weigh less. And the reason is because your basal metabolism will kick in during the night, and you will lose about 80% of your body weight through basal metabolism. However, if you're trying to lose weight by exercising, only about 12% of the food that you take in is utilized in your bodily activities. So the vast majority of your, even if you're just laying there, even if you're laying there and they're feeding you through a tube and you're in a coma, you're not really going to gain a whole lot of weight. Probably you're not going to gain any weight at all because your basal metabolism is kicking in and maintaining you while you're in your coma. You don't have to be active in order to lose weight. The body uses glucose as an energy source and so breaks everything eaten into this form. And if it can't break down into glucose, then it's not food. It's not food. And so what happens to it if you consume something that isn't food, something that can't be broken down into glucose? What will happen to it? Well, it'll pass through your digestive system and you'll deposit it out as a solid waste. Glucose is stored in the body in the liver as a substance called glycogen. When ingested glucose is low, the body will release glycogen from the liver to keep the brain functioning. The release and breakdown of glycogen from the liver is controlled by two enzymes from the pancreas. Glucagon promotes the breakdown of glycogen to glucose in a process known as glycogenolysis, and insulin promotes the conversion of glucose to glycogen. When an individual has been without food for a prolonged period, either forced or due to dieting, they begin converting their adipose tissue into glucose in a process known as glyconeogenesis. At the same time, they will produce a secondary fuel called ketones, which can be used by the body and brain as fuel. Now, the interesting thing about ketones, if somebody has diabetes, one of the first things that will happen is that they will start having bad breath. And the reason they have bad breath is because they're not able to break down the glucose and they're creating ketones. And ketones have a relatively foul odor. So if somebody is diabetic and you haven't identified them, if they have bad breath, a lot of times that is the ketones, as weird as that seems. So if somebody's on a diet and they're burning their body fat, you can smell it on their breath as ketones, as weird as that sounds. Long-term energy stores are in the form of fat cells or adipose tissue. Adipose tissue can be used for energy when the ready amount of glucose in the system has been depleted. And this is usually how people are trying to lose weight. They're trying to lose weight by limiting the amount of food that they're taking in, burning as much energy as they can, and as soon as they burn up all their glucose, then they'll start burning fat. That's what they're trying to do. They're trying to reduce the amount of adipose tissue or reduce the size of the adipose tissue. A cell of fat, of course, as you burn it, it gets smaller and smaller and smaller, and that's really what you're trying to do. The reality is if you have a select number of fat cells, you're not going to lose those fat cells. Those fat cells will stay with you the rest of your life, but you can make them as small as you possibly can. And that's what dieting is all about, and exercise is all about, is reducing the size of those fat cells. Adipose tissue can be broken down into simpler forms, fatty acids and glucose. Glucose is brought into the individual cells through glucose transporters in the cell membrane. Glucose transporters can only function when they interact with insulin, except for brain cells which do not need insulin to function. Otherwise, diabetes mellitus would cause such severe brain damage that it would be instantly deadly. There are three phases that the body goes through, must go through to be able to utilize glucose in the diet: the cephalic phase, the digestive phase, and the absorptive phase. The food itself acts as a stimuli. Seeing the food is a stimulation, smelling the food, and tasting the food. This evokes a conditioned release of insulin in anticipation of glucose arrival in the blood. In this phase, the release of insulin is regulated by the brain and is thus referred to as the cephalic phase. The digestive phase, in the digestive phase, food entering the stomach and intestines causes a release of gut hormones. This stimulates the pancreas to release more insulin. During the absorptive phase, glucose enters the bloodstream, and special cells in the liver, the glucodetectors or glucostats, detect circulating glucose and signal the pancreas to release more insulin. Insulin allows the body to either utilize the glucose immediately or convert it into glycogen. The nerve that passes information from the liver to the brain and back to the pancreas is the vagus nerve. The vagus nerve runs to the nucleus of the solitary tract in the brainstem. Diabetes mellitus is a lack of insulin causes a disease called diabetes mellitus. Type 1, juvenile onset diabetes mellitus, the pancreas stops producing insulin. Though the brain can still utilize the glucose from the diet, the rest of the body can't and so utilizes fat stores instead. Since most of the dietary glucose cannot be used, it passes through the system and is excreted in the urine. Glucose can also not be converted to glycogen and stored in the liver. Diabetics are hungry because the body tells them to consume energy, but they can't gain weight because they do not store glucose as fat. Treatment is to provide exogenous insulin. Exogenous means, of course, outside the body. So they need insulin from an outside source. And what we use today is synthetic insulin. I think once upon a time we used sheep insulin. That was a long time ago. Diabetes mellitus type 2 is adult onset diabetes, is a milder form of diabetes that usually does not affect an individual until they are adults. There are two causes of this type of diabetes. The cells gradually lose their sensitivity to insulin. The body gradually decreases its production of glucose. This type of diabetes is more common among obese people and can usually be controlled by reducing the amount of glucose in the diet. The individual can also take medications that stimulate the pancreas to produce more insulin, and that is metformin. Many people prefer the taste of the foods that they grew up with. People are drawn to sweet foods and fatty foods because their taste is satisfying. People are also drawn to salty foods because we need the sodium chloride to maintain homeostasis. People who are hyperhydrated might actually crave salt. People develop taste aversions to foods that poison them and make them ill, and this is known as a taste aversion. Most toxins are bitter tasting. Some people suffer from neophobia, the fear of new foods. Taste aversions. So my wife does not like, what does she not like? She doesn't like coconut. She also doesn't like artificial grape flavor. Once upon a time when she was a child, they went to the circus, and while they were at the circus, she had a grape snow cone, and there was something wrong with it, and she got sick, and she vomited, of course, and since then she hasn't been able to tolerate artificial grape flavoring because that's what they used on the grape snow cone. I don't know why she doesn't like coconut. I don't know that she's ever thrown that stuff up. Once upon a time, when I was working in a factory making automotive pumps and parts, my first wife made Mexican hamburger helper. And at that time, Mexican hamburger helper was, it was kind of like taco meat with Doritos. They had unsalted Doritos. Of course, at that time, there was no such thing as Doritos. There was something wrong with the meat. There was something wrong with something. Anyway, I got sick the next day and I vomited a lot. And ever since then, haven't been able to eat. I hadn't been able to eat. I can now. I mean, that was almost 60 years ago. I couldn't eat Doritos. I couldn't eat Doritos or corn chips. Anything that was made out of corn, I couldn't eat it because any chips that were made out of corn because I had gotten sick. I had a taste aversion for corn chips, as weird as that is. One of the hormones released in the stomach and intestines is cholecystokinin, which comes from the gallbladder. Cholecystokinin is released if foods have a high content of fat and or proteins. Cholecystokinin also stimulates the pancreas to release insulin. Cholecystokinin may be one of the satiety signals. However, to inject cholecystokinin into someone as a means of controlling hunger causes nausea and cramping. Cholecystokinin in the presence of food activates the muscles of the intestines to work. Absence of food leads to feelings of nausea and cramping, and that's one of the reasons why you can't do that. You'll make the person sick. Hunger triggers low insulin in the blood. These are hunger triggers. Low insulin in the blood is an obvious trigger to eat. However, high insulin levels do not equate to satiation. Satiety appears to spread over various regions in the brain, including the amygdaloid nuclei, the frontal cortex, and the substantia nigra. And you may wonder, why in the world have they done so much research on this? It's because of the obesity problem we have in the United States. We are trying to figure out some way, some magic pill we can give people to make them lose weight, to make them feel satisfied. And the answer is, we haven't found that magic pill yet. Leptin is a protein produced by fat cells that is secreted and informs the brain that the individual has had enough food. Obese people seem to be insensitive to leptin's message, and that is why they eat to excess. When leptin reaches a hypothalamic arcuate nucleus, it suppresses the release of several peptide neurotransmitters that induce eating. Neuropeptide Y and agouti-related peptide. Now, where in the world did agouti-related peptide come from? I'm going to show you an agouti in a minute. That's what they discovered. They discovered that they were doing research looking at rodents, and they realized that there was a rodent in South America called the agouti, and the chemical structure was very similar to the chemical structure in this rodent. So that's how they discovered it. Leptin also enhances the release of the peptide alpha melanocyte stimulating hormone. And let me show you what an agouti looks like. It looks like a big rat, a big long-legged rat. That's what tailless rat. I have seen an agouti. We were in Central America, and they have agoutis down there, and we saw agoutis. They don't really look like rodents when you see them. That looks more like a rodent. They're big. They're like they're about the size of a large cat. They're about the size of a small dog. They're pretty big. Anorexia nervosa and bulimia nervosa are two disorders of hunger management that leads to extreme emaciation and even death. That's especially anorexia. Bulimia rarely causes death. Anorexics commonly desire and think about food but deny themselves sustenance. The basic problem seems to be a distorted body image where the individual sees themselves incorrectly as overweight when they are actually thin to the point of death. Anorexics tend to be slender of build to begin with, and the excessive dieting merely adds to emaciation. And I'm going to show you some pictures. There you go. That's how skinny those ladies can get. Well, men are anorexic too, but it's more frequently a female problem. Bulimics tend to be a little plumper than anorexics. Bulimics are able to control their weight by purging the food from their system, either through exercise, vomiting, or laxatives. Bulimics will also go a little crazy from time to time and eat massive amounts of food at one sitting and then relieve themselves of it through vomiting. This is known as binging and purging, and that is the end of the chapter. So you guys stay safe, be good. I guess you're still on lockdown. So hopefully things will get better. We seem to be having a COVID-19 surge in the United States right now. So stay safe and stay with your family. Don't go out and do crazy things. That's why this surge is going on. Anyway, so I'll see you guys next week.